L2 fragmentation is one of the biggest challenges that Ethereum faces today. This challenge exists because the Ethereum community realized that not everything can fit into one computer. And just like anything else that scaled within the history of the internet, you need to distribute load among many different servers. In other words, in order to bring billions of users to Ethereum, we need to scale horizontally. But this horizontal scaling, with each L2 being in its own domain, so to say, has led to some really messy user experiences. If you've ever bridged assets across chains or dealt with multiple versions of the same token across these different chains, in this case ETH, you know exactly what I'm talking about. In this video, I'll cover the current industry's approach to solving fragmentation, but also introduce you to Socket Protocol, which offers this comprehensive framework for applications to overcome those challenges. I'll cover Socket's architecture, but I'll also get practical by showing you how we could build a chain-abstracted application on top of Socket. Alright, so let's get started by covering how the industry currently approaches this issue of fragmentation. First off, the good news is that many teams are working on this, and there's a growing consensus on how to simplify user experiences. Basically, we need these off-chain incentivized workers, also referred to as fillers or solvers, to compete in order to fulfill user intents. And these intents work a bit different to transactions. Traditionally, users interact through the blockchain with transactions, and these transactions tell exactly the blockchain what to do. Whereas these intents are not exact orders, but they are more like an expression to describe what a user wants. And then these off-chain workers take up these intents and abstract away from the user's perspective how they reach their goal. In other words, this setup allows these users to have their desired goals executed immediately, and from a UX perspective, not feel constrained at all by these separate domains, in this case, OP mainnet or RB mainnet. In the background, you then have some kind of intent protocol that offers a mechanism to settle these intents so that these off-chain workers get compensated for the work that they have done on behalf of the user. All right, so before we move on, I want to quickly break down the different layers of the stack that make all of this possible. So at the top layer, you would have the app and wallet layer that offers a comprehensive user experience and is responsible for crafting these intents on behalf of the users. Below that, you would have the intent protocol layer. These are protocols like Bungee, for example. They are responsible for settling these intents, meaning making sure that the solvers get compensated without them having to trust the system, and they are responsible for auctioning off these intents to solvers in the first place. Below that, you would then have the solvers. These are, as we've seen before in the diagram, these off-chain bots, and they compete economically in order to fulfill as many intents as they can in order to maximize their profits. Then at the bottom, you would have the message protocol layer. These are trust minimized systems like Hyperlane or Layer 0. They facilitate settlement by helping to pass messages across various layer 2s. And these messages in the context of settlement would contain proofs that a certain intent has been executed on a certain chain. Also, these message protocol layers are involved in various bridging mechanisms that allow solvers to rebalance their inventory across chains. Cool, so now that we have covered these foundational layers, let's dive into an actual example of a chain abstracted experience that leverages Socket Protocol. First off, Socket isn't just another cross-chain bridge, nor is it some front-end enhancement. It's a chain abstraction framework. And what that means is that it really allows developers to put their application at center stage while making any kind of infrastructure disappear to the background. As we will see when diving in detail through the Socket architecture, Socket really eliminates away the complexities that are involved in building these asynchronous systems for applications and provides app developers the perfect framework to think of these multiple chains as one single unified domain. Now, before I want to dive into the architecture of Socket Protocol and lay out how it exactly works, I want to quickly demo you the kind of chain abstracted experiences that can be built on top of Socket. And the best way to do that is to show you what the team at Enclave Money has built on top of Socket. To make it short, Enclave Money leverages a concept referred to as resource locking to offer a single unified balance. I don't want to go into the detail about how resource locking exactly works. It's a concept that was introduced by a blog post referred to as Magic Spend++. I have linked it in the show notes below, so if you're interested, pause the video here and check it out. But all you need to know for the purpose of this video really is that it allows you to treat various balances across chains as one. That is to say, for example, you have 100 USDC on Arbitrum, 100 on Optimism, and 100 on Polygon, and 100 on Base. From a user perspective, this could be treated as a chain abstracted balance of 400 USDC. That means that from a user perspective, not only can he use it atomically as one, meaning he can swap, for example, 400 USDC for another token, as if they existed on the same layer, but also he perceives them as one within his UI. From a UI UX perspective, chain abstracted balance by Enclave Money built on top of Socket Protocol would look something like this. Here you have a wallet which does not benefit from chain abstraction. You have various ETH balances and various USDC balances. But then you can see here with chain abstraction being turned on, all these tokens unify into a single balance. You have one version of ETH, one version of USDC, one version of USDT, and so on. And then now if you want to send your balance, you can send it as a unified balance. For example, all your ETH, you can send it in one go to whoever you want to. Now this is really powerful. Next, let's dive into Socket's architecture in detail and briefly lay out how we could build such an application on top of it. All right, so let's dive into Socket's architecture. First off, Socket's architecture can be split into off-chain components and on-chain components. Let's start by kicking things off with these off-chain components. The main off-chain component here is called the Watcher. The Watcher hosts this specialized execution environment referred to as EVMX in Socket lingo, which is basically the EVM with some special capabilities like offering asynchronous execution capabilities across different chains. Developers then deployed this app gateway smart contract to this EVMX environment that defines the logic for their chain abstracted application. You can think of this app gateway smart contract as the command center of your chain abstracted application. Here, for example, you have Arbitrum and your deployed application. And here you have Optimism and your Optimism deployed application. These applications deployed across various chains then get kind of virtualized within this app gateway. So from a developer's perspective, from this app gateway, you can read and write to these applications as if they were living in one single chain. Now, users will not directly interact with your application through the blockchain directly, but their requests would go through the app gateway, and the app gateway then prepares instructions that get relayed on-chain, as we will see in a second. You might be wondering how this EVMX environment handles all this asynchronous execution across chains. And that's totally natural because normally we are used to async within a JavaScript context. But you don't really need to care about this because all of this has been completely abstracted away from you by Socket Protocol. And one really cool side effect of you being able to build your app gateway logic on EVMX is that one, you can write everything in Solidity, which is the same language with which you have written your applications. And second, you can use any kind of tooling like Foundry out of the box. To finish off with the Watcher, besides hosting your app gateway via EVMX, it also monitors blockchain events on these various chains on which your application is deployed and generates proofs or attestations that get relayed on chain that these switchboards can then verify. But more on these switchboards later. But now back to these instructions that get prepared by the app gateway and that need to be relayed on chain somehow. This is where these transmitters come in. And across the industry, there are various terms used for them, such as solvers, relayers, or fillers. But essentially what the Watcher does through EVMX is to emit an event to which these off-chain actors listen. And that event kind of signals, hey, here's an opportunity to make money by completing a job on chain. Who wants to take it on? And these off-chain actors then bid for getting the job assigned to them and receive a compensation later on for completing it. Importantly to note is that these transmitters don't necessarily need any trust assumptions because, as we already mentioned, the Watcher provides an attestation or some proof that gets then verified on chain through a switchboard that guarantees that it's the rightful transmitter that is executing an action on behalf of the user. Speaking of trust, these watches actually don't need to be trusted either. They can, for example, generate zero-knowledge proofs to prove the execution that has been executed within this environment, or run within a trusted execution environment, and so on. Trust really is a spectrum, and it's up to applications to decide what kind of trust assumptions they want their users to bear. Okay, so now that we've covered the off-chain components, let's move on to the on-chain components. At its core is the socket contract, which is deployed on every chain. Here on the left side, we have Arbitrum, and on the right side, we have Optimism for illustration purposes. Now, the socket contract acts as the central router for incoming transactions. It has two main roles, if you want. First, it forwards these payloads that were crafted by the app gateway and relayed by the transmitters to the relevant switchboard. The switchboard, depending on its implementation, then verifies whatever was submitted to it. It could be a proof, it could be a signature, and then validates whatever was given with a simple Boolean back to the socket contract. Finally, the socket contract then routes the payload to be executed to the relevant application. Within socket lingo, the application is also referred to as a plug, an application plug. You can think of the switchboard here within this context as pluggable security that is fully programmable and allows to ensure that the execution that has been run off-chain here within the app gateway meets the requirements set by the application through the switchboard. One final thing that is important to mention here is that the watcher monitors the socket contract, and the socket contract emits certain events that let the watcher know that certain payloads that were relayed by transmitters have executed successfully, so that the app gateway is informed that some asynchronous calls got completed, and then some callback could potentially be called upon successful execution. For example, a callback could queue another on-chain action to be relayed on-chain, or it could trigger some update within the internal accounting of the app gateway, really depending on the given use case. This is enough theory for now. Let's actually get practical by looking at how we could implement a chain-abstracted resource locking mechanism like the one from Magic Spend++ on top of Socket. All right, so within Magic Spend++, the user has a smart contract wallet deployed on every chain. And within Socket's architecture, that smart contract wallet would be the plug, as we mentioned it earlier. Now, in this case, the smart contract wallet would have a locked balance of various tokens for the user. In this case, we have a smart contract wallet on Arbitrum with a balance of 1,200 USDC and a smart contract wallet on Optimism with a 0 USDC balance. Now, the user would come in with a request to deposit 1,000 USDC on Aave on Optimism. Under normal circumstances, without all this resource locking chain abstracted mechanism by Magic Spend++, the user would have to somehow bridge $1,000 from Arbitrum to Optimism and then deposit on Aave. But within Magic Spend++ implemented on top of Socket, the user would request that deposit on Aave on Optimism. The app gateway would then check if the chain abstracted balance across various domains like Arbitrum and Optimism of that user is sufficient to service this 1,000 USDC deposit on Optimism Aave. Remember, the app gateway has this unique ability to virtualize on-chain contracts, and hence it can very easily read from each of these smart contract wallets how much balance of locked tokens there is. So in this case, the total global balance or chain abstracted balance is a total of 1,200 plus 0, which is the 1,200. Hence, the user has enough to deposit $1,000 on Optimism Aave. So upon confirming sufficient funds, the app gateway would auction off the instruction to execute on behalf of the user a deposit of 1,000 USDC on the Aave protocol. And at the same time, the app gateway would make sure to subtract these $1,000 from the internal accounted balance in order to prevent the user from double spending, for example. So now that the app gateway has queued this instruction or payload, if you want, to be executed on chain, transmitters and solvers are aware there's an opportunity. They then bid on being able to execute the deposit on the user's behalf, and whoever wins is allowed to relay it on chain. Now, from a UX perspective, this is awesome because the user sees his chain abstracted balance of $1,200 being deducted $1,000 exactly as intended. And instead, he is now the happy owner of a $1,000 Aave position on Optimism. Worth noting is that in the setup, the user hasn't interacted at all with the source chain Arbitrum, unlike in traditional bridging, where he would have to interact with the source chain. But instead, the user simply makes a request to deposit 1,000 USDC on Optimism, and that request gets executed at the speed of Optimism itself. Now, the transmitter, solver, relayer, or whatever you want to call him, has provided the liquidity on the destination chain to execute the 1,000 USDC deposit on Aave, and obviously wants to claim them back now, plus be compensated for it with a small fee. And this is where the monitoring comes in. The watcher in this case would have monitored successful execution of those deposits and not only updated internal balances here, accounted for within the app gateway, but also generated a proof for the transmitter that it would allow the transmitter, in this case, to relay this proof to Arbitrum, where he would be able to claim back the 1,000 USDC plus a fee from the user's locked tokens. I don't know if you can recall from earlier, but this process of claiming back from those locked tokens is what we referred to as settlement earlier on when we were talking about the intent protocol layer. The type of proof here required for settlement depends really on the application-specific needs. These switchboards, as we have already mentioned, are really designed to be generic and flexible, and it's up to developers to choose the kind of settlement that they require. For instance, developers may opt in for a very trust-minimized setup, such as using zero-knowledge proofs, or a setup where trust assumptions rely more heavily on the watcher, where a simple signed attestation would be sufficient. But this really sums it up in terms of the socket protocol architecture and how you would build a Magic Spend++ use case on top of it. But as you've seen, socket protocol really is super generic, and it's really up to the application developer to choose what to leverage it for. Sky is the limit here, and I hope this video kind of helped putting things into context. Happy innovating.